So are there any questions from last time? Okay, let me remind you where we were last time. Yeah? Last time we discussed the vacuum, okay, and the vacuum was the state which was annihilated by all the annihilation operators, okay, sorry, just 1 second. Let me. The vacuum was the state which was annihilated by all the annihilation operators, and then we discussed the Hamiltonian, which we normal ordered. And it also had the property that H0 was equal to 0, okay, after we had normal ordered the Hamiltonian. Okay, and then we discussed on top of that these one particle states which were obtained by acting with a creation operator on the vacuum, we call P. Okay, and these one particle states had the property that H and P was omega pp, which means square root of p squared plus m squared on p. Okay. And p on p was just p times p. As somebody pointed out, this is an operator and this is an eigenvalue. So this is a number, this is an operator. Yeah. So that's my capital and small. Yeah. And this, if you look at these properties of the state, this dispersion relation, this relationship between momentum and energy is exactly the energy, is exactly a dispersion relation that's obeyed by single particle states. Okay. So this is obeyed. So this leads us to interpret P is a single particle state, okay, of momentum P. And notice we are not declare, you can think of this as an interpretation, but the point here is that because the momentum and the energy of the state obey this relation, and because only single particle states obey this relation, no other states obey this relation, that's why we are saying that P is a single particle state of momentum P. Okay, so this is where we reached last time, right? So are there any questions about this? Okay, good. Let me say something about the normalization of these states. Okay? So these states, in fact, let's just check what their normalization is. So if you look at P prime, okay, that looks like okay. And to do that, you have to normalize, you have to move the annihilation operator to the right. Okay, and you can do that. You see how this comes about? You see, this is the adjoint of, this is the bra that corresponds to the ket P. Okay, the ket P has a creation operator that acts on it. Therefore, the bra P has it's like the annihilation operator acting from the right. Okay. Okay. But now notice this you can write as okay, up to a commutator. This is just an identity, right? I can always flip the order of the operators up to a commutator. But now notice we know what this commutator is. Okay, and we also know that in this case, this AP acting on 0, annihilates it. I'm going to open the windows. So the AC is off, right? Well, it doesn't seem to be working anyway, but maybe I'll just open the windows. That's fine, right? I have a bit of a cold anyway, so. Like a still day. Okay, so this AP acting on the vacuum gives you 0. Okay, so this part gives you 0, and you're only left with this part, right? And so that you see gives you 2 pi cubed into delta cubed of p minus p prime. Okay, so that's the normalization of these states. Okay, so these states by themselves are not normalizable. If you ask for pp, that's just delta cube of 0. That doesn't make any sense. Okay, so normalizable states are wave packets. Which means you look at, let's call the state f. Okay. Okay, and then you can integrate. You know, the fact that I put a 2 pi cubed here is kind of irrelevant because I could have absorbed that into a normalization of this f. Okay. And if you do that, then you will find that, you know, f prime, okay, just by using this relation, looks like f star p, f prime p into d3p by 2 pi cubed. Okay. So if you choose, I think I got that right. So you know, if you choose f to be some nice function, some smooth function which has support over some range of p's, not a delta function, then this will be something that has norm 1. Okay, so normalizable states are wave packets of this kind. Okay, so that's what we want to say about one particle states. Is this clear? Okay, are there any questions about this, or? Let's see the. Okay, good. Now, you might have said in quantum mechanics, this is all that there was, right? You are often dealing with one, you know, every formula that's up here, right, which has to do with the properties of one particle states. You know, in the beginning of this course, we discussed some naive attempt to construct relativistic one particle quantum mechanics. And in fact, the states P that we constructed there were precisely of this kind, right? I could have constructed these kinds of states which had energy omega P, which had momentum P, and you know, they were normalized this way, and you could construct normalizable states. So you know, in the first lecture of this class, or maybe this, yeah, first lecture, we discussed this construction of single particle quantum mechanics, right? And everything there would have been true, and of course we found that theory was inconsistent. It didn't make sense. Okay, and in fact, it's important that in field theory, these are not the only states. Okay. Okay. So what are the other states you can get? Well, you know, it's clear what the other states are, because you see, if you look at the vacuum, we can only raise the energy from the vacuum. So what can we act with the vacuum? What, you know, what are we allowed to act with the vacuum on? So we are allowed to act with the vacuum on one annihilation, one creation operator. We did that. Now let's say I acted once more with some annihilation operator, right? Let's say I acted with, I have this state, and then I can act with more operators on it, right? Okay, what else could I act with? Let's say I acted with this. What would happen? If you acted with this, right, you know, you could use the same trick of commuting things, and you would find that this guy, you know, just looked like 2 pi cubed into delta of p minus p prime on the vacuum itself, right? So it's not a new state. It's the vacuum with some delta function. Okay, what else can you do? Well, obviously, you know, the other thing you can do is you can act with one more creation operator, right? So you can act with AP1, AP2 on the vacuum. This is a new state. It's orthogonal to the vacuum itself. You can check. It's also orthogonal to all one particle states. This is a new state. Okay, and you can check it's a new state because, you know, if you look at this, what is this? It is 0, right? Why is it 0? Exactly. You see, because AP acting on the vacuum is 0, that means AP dagger acting from the right on the vacuum is also 0. Okay, so this is 0. How about When what? Good. So it will still be 0. It will still be 0 because if you look at what this is, this looks like some AP1 dagger, AP2 dagger on 0. Now, maybe you can commute one of these through, right? But you can't commute both of them through. You'll still be left with this. So this is also equal to 0, right? So what that tells you is that this state, that's why I'm saying it's a new state. You know, when you say it's a new state, you mean it's orthogonal to the states that we had before. What were the states we had before? We had the vacuum, then the board on the top, and then we had those one particle states. And now here are some states which are new states, which are two particle states. Okay? And these we can call two particle states. Okay. Why are the two particle states? Good. So you know you can once again ask what the energy of these guys is. Okay. And the energy of these guys. So you can ask first what the total momentum is. And then you can ask what the total energy is. Okay. Oh, sorry. And this is the dispersion relation that's satisfied by two particle states. Okay. So these are two particle states. Okay. Okay. Now we found a new class of states. That's one particle. We found the vacuum. We found one particle states, and now we found some states which look like two particle states. Okay. Okay. Let me point out something very important here, which in fact, as I said, might be one of the key things that field theory tells us. Huh.
Right hand side there will be the state itself, right? Instead of when you are acting by P operator, so in the right hand side.
What?
It's not vacuum in the right hand side of the equation.
Oh yeah. Thank you. Yeah. It's not vacuum. Actually, I'll introduce some new notation. Thank you. Yeah. Thank you. Yeah. Okay. So I now define this to be P1, P2. Okay. Now I wrote P1, P2, but I wasn't very careful about what order I wrote it in. Right? I wrote P1 on the right here, P2 on the left here. Here I wrote P1 on the left and P2 on the right. Okay? In fact, there's a key property here, which is that P1, P2 is equal to P2, P1. Okay. And the reason for this is that these operators, they commute with each other. Right? Is equal to AP2 dagger, AP1 dagger. Okay? Remember, this comes from the commutation relations that we found. Okay. So these particles obey bosonic statistics. They are identical particles. This tells you that if you look at a two particle state, which has it doesn't make sense to say this particle has momentum P1 and that particle has momentum P2. Okay, there's a two particle state in which one particle has momentum P1 and one particle has momentum P2, and the two particles are not really distinguishable. Okay, saying that this particle has P1 and this particle has P2, that state is the same as the one where you say this particle has P2 and this particle has P1. Okay, so it's really important that these states are not distinguishable. And all you can say is that there is one particle with momentum P1 and one particle with momentum P2. And it doesn't make sense to say the first particle has P1, the second particle has P2, or vice versa. Okay. So these states obey bosonic statistics. Okay. And this comes out automatically from the formalism of quantum field theory. It's not something that we need to put in. Remember when you do statistical mechanics, you're taught that, well, there are states which could obey bosonic statistics, there are states that could obey fermionic statistics, and there are also states where you can think of distinguishable particles. Right? Here we find, there are different kinds of fields which are fermionic fields, which we'll look at later in the course. But these kinds of fields which come from bosonic fields, these kinds of states which come from bosonic fields, just automatically obey bosonic statistics. Okay? And remember, we discussed in the beginning, one of the important things that field theory tells us is that all electrons are the same, or all Higgs particles are the same. And it tells us that's the case because of this, because all these states which have 2 electrons here are generated by acting with some electron field on the vacuum. Okay? Or states which have 2 Higgs bosons are generated by acting twice with the Higgs field on the vacuum. Okay? And those 2 states are identical, as you see here. Okay, is this clear at this point? Okay. And this comes out automatically. Okay. So this is the second kind of states that we have, which are 2 particle states. Okay. Yeah.
So what you're doing that you're just supposing multiple momentum.
Yes.
In principle, like it should be possible to create a localized excitation.
No. Because what do you mean by localized excitation? I mean, it is possible to create localized excitation, but not by taking 1 particle states. If this is something we discussed in the first lecture. Now let's say you superpose them in some way. You could have thought, let me take e to the I p dot x, right? Let me take f of p to be e to the I p dot x. That's what you're thinking, right? Okay, let's say you take f of x to be e to the I p dot x. Then I'll get some state. I'll just call that state x. That state does not correspond to a particle sitting at x, as we checked last time. If you thought of it as a particle sitting at x, you'd run into trouble that that state has non-zero overlap in a short amount of time with the particle sitting at x prime. So that state is not well interpreted as a particle sitting at the position x. There's no position operator in that sense in quantum field theory. There is a sense in which you can speak of the momentum of the field, but this momentum that you're measuring is actually not the momentum, as we'll see in a second, as actually you already see here, is not the momentum of a single particle. It's the momentum of the state. Right? So a 2 particle state, the same operator acting on the 2 particle state tells you what the momentum of that state is. So it's a momentum operator for the state, tells you how much momentum there is in the field excitation. When you want to talk about position, positions are not additive. If you want to talk about a position operator, you want to say here is 1 particle, and then what is the position operator that acts on this 1 particle, right? So position operators don't act in this additive way on 2 particle states. There is no position operator in quantum field theory. So if you thought that, I could just superpose these states to get a particle at x, but you can superpose it. It's some state. It's not, no one says you can't take f of p equal to e to the I p dot x. It's a delta function normalizable state, but that state does not have an interpretation as a particle localized at x. Okay. Okay, good. So are there any other questions about this? Okay, very good. So these states obey bosonic statistics, and this is just automatic, right? Let me just say something about normalization. Yeah. Good. Let's just say something about the normalization of these states over here. So let's look at P1, P2 with P1 prime, P2 prime. Okay. So that looks like vacuum AP1, AP2, AP1 dagger, AP2 dagger on the vacuum. Now you have to do a little bit of algebra, okay, in commuting these annihilation operators through. So let's say you first try to commute this guy through. Okay. Then the first time you get a 2 pi cube delta of P1 minus P2. And okay, let's do the algebra. 0 times AP1 AP2 dagger 0 into 2 pi cube P2 minus P1 plus 0 1 AP1 dagger sorry, prime. Sorry guys, prime. P2 minus P1 prime. AP1 prime dagger. AP2 prime dagger. Do you see where this equation came from? I just took the AP2 and I commuted it through. Okay. When I commuted it through, I got two terms. Okay. One term was coming from the commutator. This is the term that comes from the commutator. Okay. Because I commuted P2 through P1 prime, I got a P2 minus P1 prime. Okay, into a 2 pi cube. And then I got another term where the P2 was just sitting to the right. That term is not automatically 0. It's not 0 because there is still another operator here. Okay. So if I do that, now I can do this whole step once more, and then I'll get 2 pi cubed for both of them. Okay. And here I'll get 2 pi cubed of delta of I'm not being careful with my primes again. P1, both the creation operators are coming with primes if I'm messing up this thing, and the annihilation operators are coming without primes. That's because I wrote P1, P2 and P1 prime, P2 prime. Okay. So I'll get P1 minus P2 prime and the 2 pi cubed times delta of P2 minus P1 prime. And from here, I can do this again, and I won't write the algebra, but I'll just get the other term. Plus 2 pi cubed delta cubed of P1 minus P1 prime into 2 pi cubed delta cubed of P2 minus P2 prime. Do you see how the algebra works out? It's important for you to understand this because the algebra is very simple, but so don't just copy, but make sure you're working this out. Yeah. Okay. Okay. So we've got two terms here, and that's the normalization of these states. Okay. Okay. Once more, we can consider normalizable states, and the normalizable states we have the property that we can look at states of this kind. This is just conventional. Okay, I can call this state F. I'm abusing notation a little bit because I call this state F also for the single particle case, but if you like, you can give it a different name. I just don't want to make up a different name. This is now a two particle state. I'm still denoting it by F, but it's a two particle state because the function here F depends on two different things. Okay? Don't get confused. It's not the same state as that. Yeah? Okay. Now notice something about this smearing function. Remember P1, P2 is the same as P2, P1. Right? So if F has an anti-symmetric part, that just gives you 0. Right? So only the symmetric part of F contributes. So we can take F to be symmetric. Okay, without W log is just without loss of generality. Okay, there's nothing. There's no loss of generality if you take F to be symmetric. You could make your life harder by choosing F to be some anti-symmetric part, but that just gives you 0 when you do the integral. Yeah. Okay, so that's the same thing. Everything we said about one particle states, we can say about two particle states. Just remember this normalization. Okay, it looks like this, and we have these are normalizable two particle states. Okay. Okay, good. Are there any questions about this? No? Okay, if something is not clear, I don't know how many of you have seen this before, but if I'm guessing it's new for at least some of you. If it's not clear, like stop and ask. I'm happy to explain.
These two particle states are also activate.
Yes.
They are also not normalizable.
They're not normalizable in that they're delta function normalizable. Yeah. So not normalizable is a in a strict sense they're not normalizable. The same way the position eigenstates that you have thought of in quantum mechanics are not normalizable because they're delta function normalizable.
Normalizable
By smearing them.
They have the same particular dispersion.
Yeah, they look like some superposition of two particle states. I mean, what does it mean? Will they have the same two particle dispersion? Each of the eigenstates there obeys this. Of course, the whole thing has a superposition. It doesn't have a single momentum. It has some amplitude of having different kinds of momenta. It's the same as saying if you take a single particle state of momentum p and then you look at p1 plus p2. Well, okay, it doesn't have it's not anymore an eigenstate of the momentum operator p. Okay, but it has some amplitude for having p1, amplitude of having p2. It's not an eigenstate of the energy either. It's some superposition of that, and that superposition helps to make the state normalizable. But it's not an eigenstate anymore.
Excuse me, sir.
Yeah, I was just thinking at the Zoom people on, but yeah, good.
Actually, can you please tell me that it's a naive question, but can you please tell me what are we trying to do here? Like I understood what you have done, but what are our main goal here?
What is the main goal here? Our main goal here is to construct the Hilbert space.
Oh,
We are trying to understand what the Hilbert space of the theory is. What's the
so
space?
we are starting from 2 particles and then we will go to n particle state. If I understand correctly.
Yeah, or 11 also. Yeah.
Yeah, right.
Yeah. Okay. Are there any other questions, sir?
Nothing wrong with like superposing particle states with different particles.
Yeah, you can superpose particle states with different particle number. They're in the same Hilbert space. In the same Hilbert space, you can always superpose them. Yeah, so you could consider some state which was linear combination of them. In a single Hilbert space, you're always allowed to take superpositions. Okay. Any questions? Okay, excellent. So now you see, well, now as was just said, we can go further, right? Now we did 2 particle states. Why stop at 2? Let's go further. So we can of course do higher particle states. So in fact, the first line written on this board is still true. These are not the only states. Even the ones that we've discussed so far are not the only states, right? By the way, notice everything I said here. Oh yeah, the 2 particle states I showed you, and the 2 particle states are orthogonal to the vacuum and to 1 particle states. Yeah. Good. Now, as we said, these are not the only states. Well, obviously, because we can construct 3 particle states. Right? And so on, you can construct n particle states. Okay, you can repeat the same exercise for these 3 particle states. These are eigenstates of the momentum and of the energy. They obey momentum is p1 plus p2 plus p3, and energy is omega p1 plus omega p2 plus omega p3. So I won't write it down again because it's exactly the same as the case of 2 particle states. Okay? And everything we said about 2 particle states is true. These states are identical under permutations of p1, p2, p3. So, this is the same as P1, P3, P2. There's no sense in which you can speak of the order of P1, P2, P3. Okay. If you look at the normalization, you will get, and you look at P1, P2, P3, P1 prime, P2 prime, P3 prime, you'll get all sorts of combinations. You'll get P1 minus P1 prime, P2 minus P2 prime, P3 minus P3 prime, and all other ways of pairing 2 states. Is this clear, or do you want me to work out the algebra? Is it clear how the normalization will work? It's the same pattern as we have for 2 particle states. Yeah. Okay. And the same way you can create normalizable states as well. Okay. Okay, good. So these are 3 particle states. And of course, you can create n particle states. These are n particle states. Okay, and going on all the way to infinity. Okay. This is the space of all states in the theory that we found here. Okay, why is it the space of all states in the theory? Because notice we started with the vacuum, okay, and then we did everything possible to the vacuum. You could have said, well, what if I started with 2 creation operators and then applied an annihilation operator? If you did that, you would get back a 1 particle state, right? Do you see why? Because you act with 1 annihilation operator, you can commute it through, 1 creation operator will remain, and then you'll left with the 1 particle state. Now the set of all operators in the theory, as we discussed, is the set of all possible polynomials in creation and annihilation operators. So you started with a vacuum and you did all possible operations to it, right? You acted with all operators in the theory on the vacuum. Therefore, this is now really the Hilbert space, the full Hilbert space of the theory. There are no more states. Okay. This Hilbert space is called the Fock space. Okay. You can think of it as the direct sum of the n particle Hilbert space, okay, starting from where H0 just means the vacuum, H1 means the 1 particle Hilbert space, H2 means the 2 particle Hilbert space that we found, H3 is a 3 particle Hilbert space, and so on. And you can think of this Hilbert, the full Hilbert space of the theory, as the direct sum of these different n particle states. Okay. And this has a name, it's a very important name, which is called the Fock space. Okay. Okay. Is this clear? Fock space is just a name. It's the full Hilbert space of the theory. Okay. The Fock space is a name that's used, for this kind of a free field Hilbert space. And so Fock space is a name. What we really mean is the full Hilbert space. This is the full Hilbert space. And the full Hilbert space breaks up into a number of distinct particle sectors, starting with the vacuum and 1 particle states, 2 particle states going up to infinity. And so the full Hilbert space is the direct sum of all of these different sub-Hilbert spaces, okay, with particle number ranging from 0 up to infinity. So it just means the full Hilbert space consists of all these possible states, the vacuum, the 1 particle state, the 2 particle states, 3 particles, n particles up to infinity. Okay. And this Hilbert space, this structure of the Hilbert space is called the Fock space. It's called a Fock space. Okay.
Is there a particular reason that we take direct sum instead of direct product?
Sorry, I didn't understand. Within what?
Is there any particular reason why we take direct sum instead of direct product of Hilbert spaces?
Direct
product. To construct the Fock space?
No. Why would you want, why would you want, these are conceptually different things. If you take the direct product is when you have 2 different subsystems, right? And you're taking the direct product means you're taking the Hilbert space corresponding to that. The 2 particle states are not a different subsystem from the 1 particle states. Okay? The 2 particle states are another possible configuration of the field. And the 3 particle states are another possible configuration of the field. It's not like 3 particle states constitute a different subsystem. You take direct products when you have subsystems.
Okay, so they are not related to each other. That's why we are taking the direct sum. If I'm
what do you mean they're not related to each other? The set of all possible states in the theory looks like P, f of P for all functions, plus P1, P2, let's call this F2, P1, P2. This is an arbitrary state in the theory. I mean, not writing the integrals, right? P1, Pn, Fn. This is the most general state in the theory. Okay, it's a linear combination of this kind. Can you see?
Yes, sir.
This is the most general state. This kind of state is the direct sum of the space of this and this and this. This is what a direct sum is.
Okay. Yes, now I understand. Yes. This is one definition of that state that are defined if the right hand side.
This is the most general state in the theory is a linear combination of all of these guys, and that's what a direct sum means.
Yeah. Okay, good.
Okay, good. So this is called the Fock space, and it's a direct sum of all of these guys. Okay, let me say one thing about projectors. Are there any other questions about this Fock space? Okay, good. So okay, there's something else which you should, we have these different sub-Hilbert spaces. These Hilbert spaces are orthogonal. Okay, you can also project onto any one of them if you like. So, for instance, you can look at the projector onto the vacuum. That's just this, of course. Right? Then you can look at the projector onto one particle state. Okay, why is this a projector? Well, let's check. Okay, but PP prime just gives you a delta function. So this just becomes which is P1, which is in fact what a projector is supposed to be. It's something that's by definition a projector, something with squares to itself. Okay. So this is the projector onto one particle state. As you can see, acting on a one particle state, it gives you back the same state, right? Acting on any higher particle state or a lower particle state gives you 0. Is this clear? Yeah. Is it clear that you act with P1 on something K, you get K. You see that? Because P and K will give you a delta function. Okay, good. Then you can think of the projector onto two particle states. Is this right? Okay, why don't you guys check? What if you act with P2, the P2 that I've written on K1, K2? I'll just give you 2 minutes to check. Yeah? Just check in your own notes. What happens if you act with P2 on K1, K2? Okay, just do it for yourself, and then yeah, we'll just wait for everyone to do it. Good. Okay. So did you all? Okay. So you see what happens if you act with P2 on K1, K2 is you get two terms, right? One term comes with delta of P1 minus K1, delta of P2 minus K2. But then you get another term which is delta of P1 minus K2, delta of P2 minus K1. Okay? So you'll find that this actually gives you twice K1, K2. Okay? So this is not the correct projector. The correct projector is this one. Okay. And the projector onto n particle states is 1 by n factorial. I wrote, it's 2, but what you found, but actually it's 2 factorial. You can check for higher numbers. You'll find n factorial. Okay. Okay. Okay, so that's the projector onto n particle states. And what's the completeness relation? Well, the completeness relation is that the identity is given by sum of pi, I equal to 0 to n, I equal to 0 to infinity. Where pi is the projector onto n particle states. Okay, starting with the projector on the vacuum, 1 particle states and n particle states. Okay. So that means that this is equal to 0, 0 plus this is the form in which you've seen the completeness relation often in quantum mechanics, in this form, okay? But here notice you have a different completeness relation. You have vacuum, you have this, plus one by 2 factorial okay, plus so on, plus that n term, okay? So that's the identity. If you want to insert a complete set of states, this is how you have to insert a complete set of states. Not just by putting this factor, okay, by doing this. Okay. So in the Fock space, the completeness relation looks like this. The n factorial, yes, the n factorial is because of identical particles. That's right. Okay, good now. Okay, very good. So this is what I wanted to say about the Fock space. And this Fock space is very important. And this is the Fock space we will study for most of our course. Are there any more questions about the Fock space and completeness relations? Let me just remind you what we did. Okay, we started with the vacuum. Then we said you active with one creation operator, you get 1 particle states, which we identified the momentum and energy. Then you can act once more, you get 2 particle states, and so on. N times you get n particle states. There's some completeness relation that you get, and the full Hilbert space is the sum of all of these sub-Hilbert spaces. Okay. Very good. So okay, so this is as I said is the representation of the Hilbert space that we are going to use for most of the course. However, I want to discuss another representation, sometimes called the Schrodinger representation, which is useful. For many purposes, and often when you study path integrals and so on, it's useful. We won't use it so much in this elementary course, but I want to introduce you to it because you should see what it is. So the rest of this lecture, like the remaining 45 minutes or so we have, is a bit of an aside from the main thrust of what we're going to do in this course. What we're going to do in this course is basically look at this Fock space and see, what happens when you generalize it to the interacting theory, and then try and understand, transition amplitudes between one set of states and another set of states, and analyze them in great detail and understand the S matrix. and understand various other properties of the field theory. Okay. However, there's another representation of the Hilbert space that's useful to understand, which I'm now going to explain. Okay. This is called the so this is called the Schrodinger representation sometimes. This is just a name, okay? One book where this is discussed is a book by Hatfield, okay, which is called QFT of particles and strings. Another book where this is discussed is a book by Polchinski on string theory. That's a hard book to read, but at some point, I think in chapter 2, there's an explanation of what the Schrodinger representation of states is. Okay? There are other places where you'll find it, although in Peskin and Schroeder and also in the Coleman notes, this is not discussed at all. Okay. So the point is the following, right? We have represented states in this Fock space. However, I told you at the beginning that field theory was basically just quantum mechanics. Right? There wasn't anything new about field theory. There wasn't anything conceptually new when we did quantum mechanics of field theory, right? And you could have said, well, the way we were taught quantum mechanics in not in high school but in college was, we were taught in terms of wave functions, right? And where's the wave function here? Now, of course, you can construct some wave functions by thinking of superpositions and write down some wave functions there. Always write down a wave function when you have a set of states. But there's something more direct you might have thought you could do, which is you identify the different degrees of freedom in the theory, and you just directly write down a wave function that tells you the amplitude for the field to be in a given configuration. Okay. So let me remind you, we started our quantization procedure through these commutation relations, right? And the justification for these commutation relations was, we said, look, these fields phi at a given time slice, I'm writing t equal to 0 here, you could have taken any time, are really the fundamental degrees of freedom in the theory. Okay? And then you have their conjugate momenta. Do you remember that? Okay. Now, whenever you have a situation of this kind, remember the other way we explained this was we said, well, you could think of a lattice and you could think of the fields living on different points in the lattice. And then the discrete version of these commutation relations is just phi I pi j is equal to I delta ij, right? Do you remember this discussion as well? Okay. Now, therefore, there is a very natural way to also represent states, and that way is just to think of a wave function on these different degrees of freedom. Okay. So another representation of states is to think of just a wave function of this. Okay. This is sometimes called a wave functional. Although it's fine if you call it a wave function at least. Okay, some people are very particular about the fact that it's a functional and not a function, but okay, it's really doesn't matter. Okay, what is this wave functional? What does it do? Okay. What does a wave function do? You give it some value of x, okay, and the wave function gives you a number, gives you a C number, right? So in quantum mechanics, you study these kinds of wave functions. They're like machines, right? You input x. Right? That's what a function is. This functional is something where you input a field configuration Okay, this is the input. And the output is still a C number. Okay. You see, the basic rule of quantum mechanics is that if you have the degrees of freedom, then you can think of, some function on those degrees of freedom, which assigns an amplitude to every possible configuration of the degrees of freedom, and that's a representation of the state. Right? That's how we are first taught to think about quantum mechanics, and that's perfectly valid in field theory, except that the possible field configurations that we have consist of functions. Okay? The field configuration itself is a function of 3 space. Notice you don't give the field configuration as a function of space time. You give the field configuration as a function of 3 variables, x and 0. Okay? And then the wave functional tells you for that field configuration, okay, this is only space. So field config in space, not space time. You give me a field configuration at an instant of time. That's a state, and corresponding to that, this wave functional gives you a number, which tells you what's the amplitude for the field to take on that configuration at that instant of time. Okay. So this is also a valid representation of the state. Okay. What's an example of such a functional? Basically anything you can write down. For instance, let's say I wrote that's a valid functional. That's allowed. That assigns a certain field. That assigns you give me a number phi. It'll assign some number to this. Okay, that's allowed. This is also allowed. Okay, this is also allowed, and so on. Right? Basically, you just write down any function or any functional of the function phi of x0, and that's a valid wave function. Okay. Okay, is this, yeah. How will what? How will phi squared give you a value? Good. Thank you. Good. That's a good question. So I should have used slightly different notation. Okay. For instance, you can pick out the value of the field at a point. Okay. At a point y. This is a point which I chose. Like it's a point which I like. Y. Okay. This functional, what does it do? Let's say you give it a field phi. It takes phi of x0, it squares it, integrates it, gets some number here. Also picks out the value of the field at the point y, okay, and multiplies it with that. That's allowed. Okay, so that kind of a function is also allowed. Yeah, the constraint is of course always that it should be normalizable. Okay, so if you start writing down functions which have 1 by phi or something like that, those are badly non-normalizable. If you wrote down plus here, then that's not a very normalizable function, and so that's not allowed. But otherwise, there isn't any constraint really on these set of functions, apart from the fact that they must be normalizable. This state phi of y, the way I wrote by the way, is not normalizable. Okay, so maybe I should have written something like this. Okay, and then in this limit where I take f of y to become a delta function, it will become the state I wrote. Okay. But if I wrote something like this, then it would be a normalizable state once again, where this f was a suitably nice smearing function. Okay. Okay, good. Is this concept clear? The fact that you can represent states also as wave functionals in this way? Yeah. Okay. Let's now understand how the momentum acts on this wave function. Right? You see, what does the momentum do? The momentum is the operator that satisfies these commutation relations, right? In fact, we've already worked out how the momentum has to act. You already know how it has to act, and I claim that you write pi of x0, okay, as minus I delta by delta phi of x0. So the way the momentum acts is by means of a derivative on the field, on this wave function. Okay. This kind of derivative is a functional derivative, which means you vary the field a little bit at this point, okay, and you ask how much the functional varies. Okay. So let's check that this gives you the correct commutation relations. If it does, then that's it, right? Because that's what basically defines phi. If it has the right commutation relations with phi, you're done. You shouldn't be surprised by this because remember in non-relativistic quantum mechanics, you represented the momentum as d by dx. Here the degrees of freedom are these phi of x's, and therefore it's not surprising that the momentum when you think of wave functionals looks like delta by delta phi of x. Okay, let's check that this works. Okay, so what do we want to check? Let's first act with phi of x let me just to avoid writing phi of x0 write psi of phi. Okay, if you like in your notes you can make it psi of phi of x0. Okay, the only reason I'm writing x0 everywhere is to emphasize this important point that the field configuration is not in space time, it's in space. Okay. Okay. So with the guess that we have, this looks like that's the guess that we made, right? That's the guess that's hidden a little bit below that. Now here we just use the rule for how derivatives act on products. So one time the derivative acts here, and that gives you minus I delta of x minus x prime. Okay. Sorry, let me add 0 here. And then we get into psi of phi. Okay, and then we get one more term which looks like plus phi of x prime 0 into minus I delta by delta phi of x0 on psi of phi. Right? Is this clear why this happens? Right, because the derivative first acts here and then it acts here. Good. But now this is minus I delta of x minus x prime psi of phi, okay, plus phi of x prime 0 pi of x0, right? Do you see this? Because this is just pi, right? But then this is the correct commutation relation because this tells you that pi of x0 commutator with phi of x prime 0 acting on any wave function. I didn't assume anything about what this wave function is, right? On any wave functional psi of phi is minus I delta x minus x prime on psi of phi. You see how this comes? I just take this term and subtract it. Right? But that tells you that this commutator is equal to this because if this is true for any wave functional, this must be true as an operator. That tells you pi phi is minus I or phi pi is plus I, which is what we want. So do you see why this is the correct representation? This thing that's hidden here is the correct representation of the momentum operator on these kinds of wave functions. Okay,
So when we think about wave functions where x is a continuous quantity, then like phi is supposed to be an operator, right? So how
well, phi here is not an operator. Phi here is just a function. It's just a number. Okay? You see, that's like saying x is an operator, but you think of the wave function of x. But that's what you mean is the wave function is, you see, x is an operator in the theory. Okay? But there's also, when you think of psi of x, x is just a number that you give it, and psi gives you out another number. Okay? So it takes in one number and gives you out another number. Here, you think of the field configurations as just ordinary functions, and then psi acts on those ordinary functions and gives you a number. Okay, is it clear? You can also think of an operator phi in this language. What would be an operator phi in this language? It would be exactly like the kind of operator that you write down in in position space. You see, if I give you a wave function, then you can think also of an operator x, and the way it acts on the wave function is it just multiplies it with x. And that's exactly what this phi operator is doing here. So maybe this was a confusion. You see, what we are trying to compute here was maybe I see where the confusion arose. I should have been more careful. What we are trying to compute here is the commutator of two operators, right? The way this operator phi acts on psi is just to multiply it with phi. Okay? It's the same way as the position operator acts on a wave function, is just to multiply it with x. Do you see? How does the position operator x act on psi of x? It just multiplies it with x. So the way this operator phi acts on psi is just multiply it with this way. And then pi acts this way. So there is also an operator phi, and the way the operator phi acts is it multiplies it. Now you're right, I should have been a little more careful in that I could have put hats on that, which I haven't done. So maybe you can do that if you like. So there is a phi here which is a function, and there is that phi there which is outside, which is an operator. Okay. If you want to disambiguate for yourself, please put hats on that phi and that pi, and this phi doesn't have any hats.
So it's like the equivalent of like we have in quantum mechanics position. Like
exactly.
Here the eigenvalue is a function.
Exactly. Yeah. You can also think of eigenstates, which are some non-normalizable states, where this function basically gives you a delta function. So it's like a product, it just forces the configuration to be some particular thing. Okay. Okay, is this clear? This might be a little unfamiliar, but in fact, if you think about it, if you ever get confused about this, just go back to a lattice formalism, where you have these different fields I at different points. And then what is this wave function? It's just a function of those, those phi i's. So it's not something, it's actually what you should be more familiar with. Maybe some of you have seen quantum field theory before, so you're more familiar with the Fock space. But in fact, if you were just doing quantum field theory for the first time, if you were in 1930 and you were trying to develop quantum field theory, you might have naturally said, well, that's obviously the Hilbert space we should write down. Okay. Now, it so happens that the Fock space is more convenient for many purposes. This is also convenient for some purposes, but the Fock space is what's most naturally used and used to understand the S matrix and where most of the literature is. But this is perfectly fine. There's nothing wrong with thinking of the Hilbert space in this language. Okay. And then phi acts this way and pi acts this way. Okay. Okay. Now let's just make some connection with what we did earlier. And the connection I want to make is I want to understand what the form of the vacuum is. Okay. So I want to understand what is the wave function that corresponds to the vacuum. And then we can understand what's the wave function that corresponds to other excited states as well.
Write a Hamiltonian for the time.
Yeah, sure. You can write the Hamiltonian. It's just psi squared plus pi squared.
So it will depend on like what
On what equation motion?
For
5 pi base?
5. So for Klein Gordon equation, like we can find a certain.
Well, the Hamiltonian, I mean, you have to give me the theory, but for instance, what the Hamiltonian we wrote for the free field was this, right? It's still this. The Hamiltonian not different. This is still the Hamiltonian, except you want to realize it on the wave function. This becomes a double functional derivative. It becomes d2 by d phi x squared. So how does this h act on psi? Well, this term it just goes through. Okay, this integral is over space. Okay. Plus Indeed. So that's how the Hamiltonian acts on a wave function. So like, let's say you take that psi of x0, the one we wrote in the beginning, right? Like, which was a Gaussian integral. The Hamiltonian acts in some particular way. And you give me that, it'll give you some number corresponding to that.
I actually was talking about time appreciation.
Yeah, it's this. That's it. So this is the state at time 0. You tell me a state at time 0, state at time t will evolve this way. You just put in the time dependency. You give me the state, it's like you give me psi of x, and I'll tell you this will evolve, tell you how it evolves. The Schrodinger equation is the same Schrodinger equation. As I said, there's nothing new in field theory. Field theory is quantum mechanics. So this is the Schrodinger equation. Yeah, we'll find the vacuum wave function now. Yeah. Okay, so now we are about to find the vacuum. Okay. Is it clear what we just said? Okay, so now maybe I shouldn't have erased this. You see, you could have found the vacuum by trying to find which state has h equal to 0. If you want to normalize h correctly, and you put the normal ordering. In fact, there's a slightly easier way to find the vacuum, which is to ask for the state which is annihilated. See, defining property of the vacuum is this, right? And we can use this equation, in fact, to find the wave function corresponding to the vacuum. It's a little easier than trying to find the state that has 0 h. Some of you have seen Hatfield. I don't remember if Hatfield does it this way or the other way, but we'll do it this way. Okay. Okay. Let's solve this equation, and then we'll find the wave function of the vacuum. Okay. Now it's a little convenient to move to slightly different variables. You see, I wrote psi of phi of x0, right? But alternately, let me get my conventions right. I could have defined this function I think I should warn you that some of the Fourier transform conventions, I think, in Hatfield are slightly different. Okay, so there might be some factors different between what we are doing and what Hatfield is doing, but it's okay as long as you keep one consistent set of conventions. So I can define some new, this phi is a function, and I can define this new function. Okay? And then we can think of wave functionals right? I can do that. There's nothing deep here. I want to emphasize in everything we are doing, if you just think about it, it's actually very simple. This psi, you know, it's like I'm just making a change of variables inside. You know, if I have a function of two variables, like a wave function, I can also think of a function which looks like I can change variables to some linear combination, right? Nobody can say, I can give you the function in terms of this linear combination instead of this one. That's fine. And that's exactly what I'm doing here. You know, this is still a machine that takes phi of x and gives you out a number. However, it does something in the middle. The way it gives you out, we are just conveniently writing it by saying, well, once you give me phi of x, first do the Fourier transform to get phi of p, and then I'll tell you what the wave function does for phi of p. Okay, in the end, this is still a functional of the field phi of x. You can think of it as a functional of phi of p that's completely equivalent. Do you see that? Is that clear? Okay, good. It's just, and the only reason I'm doing this is because it's convenient to solve that equation in these variables. Okay. Okay. Let's just work out. Okay, the same way as we have, you know, we had this phi, we can Fourier transform pi. Okay, but you have to be a little careful of what the phi commutators are in momentum space with this definition of the Fourier transform. You could have used different signs and you would have got something different, but here we chose to define both the Fourier transforms with a minus sign. Okay. And then you can check that if you work out, now let me write the operator. This is now the operator corresponding to this phi and pi. Okay. Then this would look like These are the hats that I didn't write earlier. Sorry, P prime dot x prime. Okay. And if you do this, this will give you a 2 pi cubed of delta of x minus x prime. Okay. And then from here, so x will be set to x prime, but you will get a minus ip plus p prime. Okay. So this will actually look like a 2 pi cube of minus I into 2 pi cubed of delta cubed of p plus p prime. Okay. So the way we've written it, the way we've defined, we could have chosen better conventions here, but the way we've defined it is that the Fourier transform is always defined with e to the minus ip. And when you do that, the commutation relation of phi hat and pi hat, these operators, becomes delta cubed of p plus p prime. Okay, not p minus p prime. Okay, and there's also 2 pi cube that we get here. Okay, so this phi, how does this guy act on wave functionals? Well, it acts like minus I into 2 pi cubed into delta by delta phi of minus p0. Okay. Huh? It is minus I. What's? Pi. Sorry. Why minus I here? Why did it become minus? Huh? There's no minus I here, right? Here it's minus I. Okay. Okay. Now let's go ahead and solve these equations. Let me remind you what we had for AP. This one? There? That came from this commutation relation.
In that same thing we did earlier in position.
You mean to check that this is correct? Yeah. If you have this commutation relation, then you know it's clear that pi has that representation. But you can check if you like by taking that. There's no I, by the way. It's delta by delta phi. You can check that there's something from an old thing that's left behind. Okay, that's nothing.
So there is x becomes I del by del p.
No. It's very important. We're not going to that kind of momentum space. There's a different thing you could have done, which is you could have gone to a field. You see, you could have done a Fourier transform of phi, okay, in terms of pi. That's not what we have done. You see, what you're talking about is, I could have done something like this: e to the I phi of x0 times pi of x0. This is the Fourier transform that you're talking about, and this would be an integral over all phi, like it would be a functional integral. This kind of thing would give you the Fourier transform and take you to a momentum space representation where pi acts like multiplication and phi becomes a derivative. That's not what we have done. Okay, I want to emphasize this momentum space. So this is the same thing we've discussed earlier. Distinguish between the momentum that's conjugate to the field and the momentum space in physical space. They are distinct things. Here we have just gone to a momentum space in physical space. We have taken x, which is the x parameter of the field phi, and Fourier transform that. We have not gone to a representation of the wave functional in terms of the conjugate momentum of the field. We could do that, but we are not. There's no reason to do that. Okay, is this clear? There's a distinct, we're using momentum in two different ways, and it's very important to be conceptually clear about the distinction between them. One momentum is the momentum that corresponds to the physical point x, okay, and then you can ask what is the operator that generates translations in that point, and then you can do Fourier transforms of functions with respect to a p, like we have done above there. Okay, so this p that appears there, we are calling momentum space, but that's physical momentum space. That should be distinguished from this pi, which is the momentum conjugate to the field. So in particular, writing the wave functional in terms of phi is still in phi space. I've not done, gone to momentum space for the wave functionals. So on this act, the operator phi still acts like multiplication, and the operator pi still acts like a derivative, as we see there. Okay, because that's the operator pi. It's really like saying, you go from psi of x1 x2 to psi of x1 plus x2 x1 minus x2. So we are not doing a Fourier transform. We could have done that, but we are not doing that. Is this clear? Yeah. So pi is still acting like a functional derivative, and phi is still acting like a product. Okay, the Fourier transform we've done is in real space, not in this field space. Is this clear? Or not clear? Not clear. Okay, what is not clear? You see, all I said was we have phi of x0, and I defined phi of p0. And I said, look, you can think of the wave functional as a function of phi of p0 instead of phi of x0. Phi of p0 is just a linear combination of the different phi of x's, right? As you can see manifestly. So it's like saying, instead of writing the wave function a function of x1, x2, I write it as a function of x1 plus x2, x1 minus x2. When you do that, the operator x1 plus x2 still acts like multiplication, and the operator p still acts like a derivative, which is what we see there. So this is not like going from position space to momentum space for the, so there are two momenta in the game we have to be careful about. One is this pi. This pi is the momentum conjugate to the field phi. We have written the wave function as a function of the field phi. We could also have thought of wave functionals of the momentum pi, as you can always do in quantum mechanics. We are not doing that. We are still thinking of wave functionals of the field phi, except we are using a different linear combination, which is that Fourier transform field phi. Okay? So we are using the word momentum for p, but that momentum is not this momentum. This momentum is different from that p. Okay, is it clear now? What? No. This is our definition of phi of p. That's just our definition. Phi of p is that, pi of p is this. This is by definition. I just chose to define new variables. Then I found that commutation relation. Then I looked at the commutation relation and I found it.
No, I'm talking about that particular form.
Of pi hat. Yeah, once you have this commutation relation, you can derive that form of pi hat the same way we derive the form of pi of x. Once you found the commutation relation of phi of pi with phi, then how pi acts as a functional derivative is fixed. The same way we first found that pi of x acts like a functional derivative delta by delta phi of x. That's how we found this. Yeah. There's no sign change. What sign change? In the denominator. Yeah, it's phi of minus p, and that's because the commutation relation looks like delta cube of p plus p prime. Okay, and there's also 2 pi cube. Okay, good. So now remember what we found. Go on, yeah.
So is it like saying we are changing the basis from x to p?
No, we didn't change the base. What do you mean by change the basis from x to p? That's what we're discussing. We didn't change the basis from, we changed the basis from a function of phi of x to a function of phi of p. It's like changing basis from a function of x1, x2 to x1 plus x2 and x1 minus x2.
Right. So like if we write a vector like ij, and then if we write a vector in r theta, so there's some one-to-one correspondence like that?
Yeah,
so we're saying that phi,
if you like, yeah, like xi and r theta, yeah, sure. You can think of the wave function as x1, x2, x3 or the wave function of r theta phi. Sure.
Yeah. Okay.
Yeah. Okay, good. So now recall what we found for AP. AP is still the operator it was earlier. This is the formula we have from earlier. Okay, it'll come from somewhere earlier in your notes. Yeah, this formula we derived earlier. But now see what this formula becomes in terms of this phi of p and pi of p. Well, it just becomes right. Is this clear? There's just, I mean, there's nothing. Yeah. Okay, now what do we want to solve? We want to solve for the vacuum, for the state that's annihilated by all APs, right? So we want to solve that's what we want to solve. Okay, what does that equation become? Well, it becomes square root of omega p by 2 phi of p0 on psi, okay, plus, now the various signs you have to be a little careful of. There's an I and a minus I, okay, and then there's a 2 pi cubed. So there's a plus 2 pi cubed the I and the minus I give you a 1. Okay, there's an I here and a minus I on top. Okay, so that's the equation that we need to solve. Oh. Yeah, it's a function of p. You can think of it as a function of x, but you can also Fourier transform to p, right? Functions of x have the same information as the Fourier transforms. Yeah. Okay, so what's the answer for this? Well, we know what the answer for this is. Let's call this psi 0. This functional equation is easy to solve. You can verify the following expression solves it. Okay. So this is the wave functional corresponding to the ground state. Notice this is a Gaussian. If you like, you can define phi of p0 as phi real of p0. I'm just breaking it up into its real and imaginary parts, p0. Okay. And if you do that, then phi of minus p0 is phi real of 1 second. And this comes from the fact that the field phi is Hermitian, right? Phi of x is the real field. So phi of minus p, okay, is the complex conjugate of phi of p. You see that? The way that's defined here on top. Yeah. So phi of minus p is just the complex conjugate of phi of p. Okay. So that's if phi I write as phi r plus I phi r, then phi minus p I write as phi r minus I phi of p0. Okay. So this you can also write as, if you like, so you can also write psi 0 as e to the minus half psi r p0 squared plus psi I p0 squared into omega p into d3p by 2 pi cubed. Okay. I haven't done anything. I just broke this up into real and imaginary parts. I used the hermiticity of phi and showed it's a sum of squares. Okay. So it's a Gaussian ground state, which is what in fact you expect the ground state of a harmonic oscillator to be. Remember, the way we were quantizing the field was by saying the field breaks up into an infinite number of harmonic oscillators. And you could have said Well, if it's broken up into infinite number of harmonic oscillators, the ground state is a Gaussian state. So Gaussian in what? Well, this is how it's a Gaussian. Okay, is it clear? So this is the solution to that equation, and this gives you an expression for the ground state. Now let me say something. This ground state we have not normalized. Okay, if you were to try to normalize this ground state, you would find, how do we normalize the ground state? Well, we normalize the ground state by dividing by something which depends on omega, right? So the normalization, and this is a subtlety and one reason why we don't use this representation so much in elementary courses, okay, would involve a product over all omega p, okay, which is not a very well defined quantity. Okay, so the normalization of the state, if you want to write it, has this product over phi of omega p. But that doesn't mean that the state is bad. It doesn't mean that the state is bad because you can forget about the normalization. You can still ask, what's the amplitude for the field to take one configuration of p as opposed to a different configuration of p? And that ratio is really what's important, right? Not the absolute normalization. Given some operator, what you're really interested in is, or given some wave functional, what you're really interested in is some question where, like this, right? Like, what is the ratio of the amplitudes for the field to take one configuration as opposed to the other configuration? And that ratio is still well defined because the normalization cancels in that. Or if you want to ask the question of some expectation value A, of some operator A, then what you need to do is look at psi of phi squared A, okay, and divide by psi of phi squared. And this ratio is still well defined, even if the normalization in front looks like it's infinity, because in all these all well defined ratios, this infinite factor will cancel out. Okay. However, this infinite factor is one reason why it's a little subtle to deal with these things, and it can be a little confusing. But conceptually, I hope it's not confusing that the ground state of the field is a Gaussian ground state, just like the ground state of a simple harmonic oscillator. By the way, you could write this expression back in position space if you like, by Fourier transforming. If you did that, you would find that what you would get here would be square root of nabla square plus m squared, because this is square root of p square plus m squared, which would become square root actually of m squared minus nabla squared of phi of p. So you can think of this as phi of x times square root of m square minus nabla square acting on phi of x again. Okay. But that's not very important for what we want. This is a perfectly good representation of the field. Okay. So this is the expression for the ground state. And of course, we can get excited states as well. What's an excited state? How do we get excited states? How do we make connection with the Fock space? Any ideas? Huh? Exactly, you operate with AP dagger, right? And then you'll get the first excited state. So if you act with AP dagger, then the wave function you'll get will look like okay. But now you'll get a minus sign into 2 pi cubed by square root twice omega p del by del phi minus p0. Okay, and in this case, these things will add up and not subtract. So this will just look like okay, so that's the first excited state. And similarly, you can find the second excited state and so on. And in fact, you will get, you can act with AP1, AP2, and you'll get psi P1, psi P2, and so on. Psi 0 is the ket 0. It is the wave function corresponding to ket 0, huh? Why? It is the wave function that corresponds to the ground state. ket and writing the wave function are just two different ways. You know, what's the confusion?
Whatever that we can write position eigengets and we can write states as like abstract vectors.
Well,
wave function is like the projection of those gets on the position eigengets.
Well, so let's say you write the state 0 for the harmonic oscillator. You've seen this. You can write it this way, and also you can write psi 0 of x is e to the minus half omega squared x squared. These are the same thing.
Psi naught of x is actually project x in a product of 0. Like a projection onto the position state.
Okay, so you can think of this as a projection of the vacuum onto some phi of p, if you want to think of it that way. Fine, you can, and then sure, you can think of it that way. You can think of this psi 0 as yes, you can think of it that way, but and that's fine. So you can think of this psi 0 as this wave function as we are writing as a projection of 0 onto state psi of p, onto eigenstates phi of p. Yeah, and then the way these operators act, you can think of them as either abstract operators or the way they act on this wave function in this way. And there's nothing different from what you do in quantum mechanics. How would you find the first excited state in quantum mechanics? Exactly this way. Have you seen the creation annihilation representation of the states for a simple harmonic oscillator? It's exactly this. You'd act with a dagger, which would look like x plus I of p or x minus I of p acting on the vacuum, and the p would act like a d by dx. So the first excited state would look like x times e to the minus half omega squared x squared. It's exactly the same. There's nothing different here and in the simple harmonic oscillator. This just looks like x times e to the phi of x, except there are many x's here. So it's not a wave function of one variable, it's a wave function of infinite number of variables. And you acted with the creation operator for one of those states, and therefore you excited one. So it's that particular x that you acted with. That's the only new thing, but there's nothing else that's new.
So I can define like another basis where eigengets are like get of like phi at p.
Yes, you can.
That is another basis, and when I project it on that defines the wave function.
Sure, you can think of it that way, or you can just think that the wave function, every state corresponds to a wave function, and the wave function is something that gives you. Yes, you can think of it that way if you like. I'm not sure why it's useful, but sure, if that's the way you're familiar with it, you can think of it that way. But you should basically be able to pass freely between wave functions and states. They're not different things. To every state, there is a wave function and vice versa. Okay, is this clear? Okay, good. So let's stop here. Next time we'll go back to the usual fork representation. I want to say that what I said in the last 45 minutes of this lecture might have been, it's a little new, so and you will not find it in most textbooks, and so it might be a little confusing. However, I would urge you to, and I also want to say, we won't use it so much in the rest of the course. So in principle, you could forget about it, but I would urge you to think about it a little bit, because it's useful. It kind of makes clear why what you're doing in field theory is not different from what you're doing in quantum mechanics. And it's also useful for many other things, when we think of gravity, when you think of path integrals and so on, to be familiar with this representation of states. Yeah? Although we won't use it so much more in this elementary course. Okay, so we'll stop here. Yeah, thank you.
The functional is for single particle excitation.
This one, yes, it's one particle excitation.
Single functional.
Yes. You take the vacuum and multiply it with 5. And I can't swear I got all the factors right, but I think I did, because if you had a plus sign, you'd get a 0, so you just multiply it. Oh, so is that fine?
It's not I wanted to interpreting the excitation as a particle, right?
Yes.
But if I wanted to obtain a wave function for that the picture not work.
What do you mean? So wave function of the particle means you want, this is a delta function. I mean, by wave function, maybe you can take this and you can project it onto single particle states. So this is a delta function on p equal to p prime. It's like what you were saying. But of course, so you can also, maybe what you mean to say is this. You can also look at f of p times this. And then f of p would be a wave function, and get an f of p on the right hand side.